Module 2.2, Theoretical Foundations of Density Functional Theory. There are two principal theorems that govern the Kohn-Sham equation and density functional theory. First one is called the first Hohenberg-Kohn theorem, which talks about the uniqueness of the ground state density. So when I say density, you will typically consider wave function squared, right? So it basically states that all ground state properties, such as the total energy of a system, are determinable from the ground state electron density. What it basically implies is electron density, which is a function of three-dimensional spatial coordinates in x, y, z directions, can replace the wave function. And instead of dealing with 3n, n being the number of variable here, 3n coordinates, we have to deal with n number of electrons only, because electron density is a scalar quantity, while wave function is kind of a vector quantity. The second Hohenberg-Kohn theorem deals with the variational principle. So it basically says that there exists a variational principle for electron density that we define in the first Hohenberg theorem, and the energy functional attains its minimum value at the ground state density. So you can variationally vary the electron density to get its minimum value, which will be the ground state. Now, basically, you can break down the total energy of a system, which is a function of density, as the kinetic energy T, the electron-electron interaction energy VEE, kind of the Coulombic energy, and the last term represent the interaction with external potential. This is a very tricky part. Unfortunately, there is no exact form of the functional that is used in DFT. So that makes it very challenging. However, these theorems are mathematically provable. Also, those theorems are profound because they shift the focus from many body wave functions, which is kind of vector quantity, to a very simple quantity such as electron density, which is easy to tackle. And that kind of reduces the computational cost. And this is why we can do some materials calculation or mechanical property prediction and so on. Now, we have to move on from Hohenberg-Kohn theorems to Kohn-Sham equations. So the Hohenberg-Kohn framework theoretically simplifies the description of electron system, but does not provide a practical way to compute the energy functional directly. So this is why they were not engineeringly or viable. So the main challenging is that while the existence of universal functional form in terms of densities is guaranteed, its exact form is not known, as we discussed in the previous slide. So this is why we need to break down this entire problem into following parts. First is kinetic energy. So kinetic energy of a reference system of non-interacting electrons, which is easier to calculate. So you can have the grid of your system, and there are some mathematical Fourier theorem based law that from which you can calculate the kinetic energy. We will not go details of that. Then the external potential energy, which is very straightforward to compute, and for simplicity we can consider as a Hartree potential, harmonic potential, for example. Now there's a Coulombic or Hartree energy. So this Hartree energy describes the electrostatic interaction between electron density clouds. Now, final, very tricky is exchange correlation energy, which captures all complex quantum mechanical principles that are not captured in the classical Coulombic interactions that are usually accounted in the exchange correlation energy. Let's look more into this exchange correlation energy. So the exchange correlation functional, so by the way, functional is basically a function of a function is called functional. So the exchange correlation functional aims to encapsulate all the many body effects of the quantum system into a single term that can be added to the effective potential in which the electrons move. So there could be exchange interactions and correlation interactions. When you say exchange interactions, these arise due to the quantum mechanical principles that two electrons with same spin cannot occupy the same spatial position, especially as a consequence of Pauli exclusion principle. So this interaction results in a form of repulsion that is not purely electrostatic. You know the like charges kind of repel and the unlike or opposite charges kind of attract each other. But there's a more beyond to that in quantum mechanical picture, and that's why exchange interactions are important. Correlation is very interesting because this describes how the motion of one electron in a system is correlated with all the other motion of all the other electrons in the system. So this how this correlated or correlation is important. So electrons try to avoid each other due to the repulsive forces, which is not captured considering only the average electron density or exchange effect alone. So this is why correlation is important. So there have been several research works to capture this exchange and correlation terms in a tractable way. So one of the first attempt was local density approximations, which basically deals with assuming a uniform electron gas at each point in space. So Thomas Fermi rule will not go in detail of that, but that's the simplest approximation. And in LDA or local density approximation, it deals with the electron density at a particular space in a system. However, it excludes the gradient or the rate of change of electron density, which is also important. And that's why there was a proposal of generalized gradient approximation called GGA, which improves on LDA by considering not just the electron density at a point, but also the gradient of electron density. And finally, hybrid functionals, which also include a portion of exact exchange from something called Hartree-Fock theory, which is more computationally expensive, but gives you more accurate properties. So these are some of them, but there could be more complicated and involved exchange correlation as well. And there have been several research work on how to find the best exchange correlation for a particular problem. So now let's get back to something tractable. So Korn-Sham equation, as we discussed a little bit earlier, is it deals with fictitious systems. So instead of dealing with a many body picture or many electron system, it deals with a non-interactive single particle picture and dumps kind of all the rest of the interaction into exchange correlation term. And it also deals with density instead of wave function. That kind of simplifies the problem a lot. So again, this is our famous Schrodinger equation where we have H psi equals to E psi, and then we have broken down into the kinetic energy term, effective potential, and this effective potential can also be broken down as the nuclear electron interaction, electron-electron interaction, and exchange correlation that we just talked about. And based on the theory you are using, there could be LDA, GGA, meta GGA, hybrid GGA, generalized random phase approximation. We'll not go in details of that for our mechanical engineering applications, but it's just important to learn about how they capture not just the density n, but also the gradient of density, the second order derivative of density, and so on. So I want to point out, although density functional theory is a complete theory, there are several approximations, such as we saw about the density of electrons in a space. So when we describe this space, the discretization of the space is very important. So usually it's done in a Fourier space or K space, and that's why the K points or the reciprocal or lattice points could be important. Also, if you're dealing with van der Waals bonded systems, it's important to capture this van der Waals interaction. We learned about that in our previous slides about different types of bonding in solids. So usually all this LDA and GGA do not capture van der Waals interaction. So if you're dealing with systems such as the hydrogen containing systems or van der Waals 2D material, then you need to capture the van der Waals interaction, and so on. There are many other approximation in Korn-Sham equation. So there is a nutshell or summary view of the DFT framework. So basically, we start with the initial guess of the electron density, and from there we can calculate the effective potential broken down into external potential, Hartree kind of Coulombic potential, and dump all the many body effect in exchange correlation term. We can solve this Korn-Sham equation, get the psi and epsilon, which is the wave function and the eigenvalue of energy. From this, we construct a new charge density based on the psi, and we try to self-consistently or kind of variously get whether the charge density is kind of converged. When it's converged, from there you can calculate important quantities such as energy, forces, stresses, and from there you can calculate such as stress strain curve, elastic constants, thermal properties, thermal conductivity, and so on. So on your right hand side, I show you a very simple picture of solving a one-dimensional Kohn-Sham equation. So for simplicity, we can take this external potential to be a simple harmonic oscillator potential, half x squared, and from there we can construct the Hartree potential for the electrons and add it to the harmonic potential, and then we do not know exchange correlation term here, so we'll try to kind of guess it from this self-consistently. So we try to solve this Kohn-Sham equation with some initial boundary condition, and rho is the initial guess that we just define on the left hand side, and we kind of self-consistently construct this effective potential, get the Hamiltonian, get the energy and the wave function, construct the new electron density, and there's a mixing term, and we try to do it until and unless we have converged the charge density, and that gives you the converged energy, converged wave function, and converged density. So I would also like to bring up some of the limitations of density functional theory. As we see, these functionals are quite arbitrary in nature. So functional can fail on different properties such as band gaps or reaction energy. So it's very important to choose appropriate functional while applying for engineering applications. Also, DFT, because it's dealing with electrons at a very small scale. When you have hundreds of atoms, we are dealing with numerous electrons, and it becomes intractable to kind of compute properties, and that's why it becomes very expensive. And this is why we have to learn about high performance computing that we'll also discuss in previous modules to kind of tackle this large scale simulation using DFT. And this also leads to solving this problem with molecular dynamics equations or classical equations that are important for higher scale and engineering applications. So, however, it's important to understand in molecular dynamics, we do not have access to exact electron cloud and so on. So molecular dynamics are usually fit to the density functional theory data, and then they can be used for Newtonian based equations.